Sure.
Just going to check if this works. Yeah. Good. So which is my command? Would you like some water?
Yes, please.
No, I only have sparkling.
Sure.
Just going to check if this works. Yeah. Good. So which is my command? Would you like some water?
Yes, please.
No, I only have sparkling.
Sure.
Just going to check if this works. Bueno, muchas gracias por haber venido. Este es el primer seminario del Laboratorio de Historia de este año, el primer seminario del proyecto Fondesit, y tenemos el honor de tener aquí a Paul Edwards. Como les decía, esto es parte de las actividades del proyecto de Historia de la Meteorología, y entre el grupo que está presente está el equipo de ese proyecto, integrantes del laboratorio, integrantes de la red CTS, y yo creo que me gustaría destacar lo interdisciplinario de la reunión, porque hay aquí hidrólogos, historiadores, historiadoras, meteorólogos, no sé, ¿quién me queda afuera? No sé, otras, pero es una gran variedad de personas que miran a estos problemas desde perspectivas diferentes, complementarias, y bueno, sin más los dejo con Carlos, que va a contar de qué se trata el proyecto. De ahí vamos a pasar a la presentación de Paul. Paul tiene lo que va a conversar Carlos, lo tiene en inglés, así que él va a estar siguiendo. Después vamos a hacer una primera ronda de intervenciones en relación al proyecto, o sea, por si la gente del proyecto quiere hacer preguntas o algo, hay que Paul responda, y luego abrimos a todos quienes quieran intervenir. Así que, Carlos, por favor. Carlos,
Spanish.
Sí, todo hablan.
Okay. Bien, muchas gracias entonces. Thank you for coming.
Great pleasure.
Y el objetivo es, como decía Cecilia, a quien agradezco por la organización y por permitir estar en este lugar, es dar un inicio, o sea, ya lo iniciamos, en realidad esto no es tan inicio, pero a un proyecto que tiene su primer año, y contar más o menos en qué estamos, cómo nos estamos organizando para este proyecto, y por eso yo voy a darnos solamente unas, this is in English, solamente algunas ideas generales de lo que nosotros estamos trabajando. Bueno, el proyecto se llama Disciplinando el Tiempo, los orígenes de la meteorología entre el 1849 y 1928. Bueno, la primera parte de todo proyecto Fondes es para engañar a los evaluadores, ¿no es cierto?, con que es algo interesante. La segunda parte es lo que realmente queremos hacer. Hay un tema acá que tiene que ver con... Es una apuesta, que es los orígenes. Es decir, en términos de lo que es la propia historia de Chile, vemos dos fases o dos hitos. 1849, cuando comienza la observación astronómica y la astronomía de los cielos. La meteorología era parte, sí, por mucho tiempo fue parte de la propia meteorología. Y en 1928, cuando formalmente se crea el Instituto de Meteorología. Entonces tenemos ese espacio. Entonces teníamos dos opciones, entre otras. La primera opción es decir, miremos cómo se formó la ciencia meteorológica, con lo cual nosotros desde hoy día definimos lo que es ciencia y dejamos de lado lo que no es ciencia, o miramos a los actores y las actrices, que también hay mujeres, cómo definen o cómo se definen como meteorólogos o meteorólogas. ¿Qué están haciendo para considerarse un departamento meteorología, un departamento dentro del observatorio astronómico? Entonces, tenemos instituciones, obviamente la Universidad de Chile, el propio observatorio astronómico, el servicio hidrográfico de la Armada, hay órdenes religiosas, están los jesuitas, están los salesianos, unos en Santiago y los salesianos en Punta Arenas. Vamos a ver un punto importante de meteorología es Punta Arenas, por las dificultades de navegación. Y también hay algunas instituciones extranjeras que hemos estado mirando. Los sujetos son distintos, son marinos, astrónomos, ingenieros, médicos, hay muchos médicos trabajando como meteorólogos, profesores, agrónomos y también los sacerdotes. No hay que olvidar que también forman este grupo. Hay instrumentos, barómetro, psicómetro, termómetro, pluviómetro, pero también formas de medición diferentes, Fahrenheit, Celsius, distintos que están, digamos, coexistiendo. Entonces, más que discutir lo que es una disciplina de meteorología y quién era meteorólogo y quién no era meteorólogo, nosotros queremos ver cómo se relacionan este grupo tan diverso entre sí, cómo forman redes, y también cómo se relacionan, ¿no es cierto?, de manera internacional. Por ejemplo, nos preguntamos, ¿hay un método que siguen para hacer mediciones atmosféricas y presentarlas, por ejemplo, de forma estadística? Son mediciones que se hacen principalmente, entre comillas, en tierra, on the ground, porque son presión, temperatura, etcétera. La mayor parte de las mediciones se hacen, digamos, no se hacen en la atmósfera como tal. Este es anterior al periodo que estudia, ¿no es cierto?, Edwards, que es donde está los satélites, y hay otro periodo muy diferente. ¿Cómo iba siendo la relación entre meteorología y clima? Que son dos fenómenos que se van dando de forma, digamos que hay una relación ahí. Los congresos internacionales, como el Congreso de Viena de 1877 o en Roma, de 1879, también tienen una influencia para definir cómo se estudia desde el estudio del clima, cómo se estudia el tiempo. Eso es una pregunta que nosotros nos hacemos. Entonces, el primer eje de trabajo no quiere determinar aquí está la meteorología, aquí no está la meteorología, no, sino que mirar todo lo que se diga meteorólogo o meteoróloga, nosotros lo incorporamos dentro de este estudio. El segundo eje, a partir de eso, examina la posición de los expertos. Y también vamos a ver las expertas. ¿Quiénes pueden ser considerados expertos y expertas? Sabemos que en algún momento la experticia tiene una relación con los medios de comunicación. Lo sabemos muy bien, ¿no es cierto? Nosotros estamos en un proceso de construcción de expertos que están haciendo una constitución. Bueno, o sea, ahí vemos lo que cualquier cosa cabe dentro de una categoría de expertos. Bueno, en fin, no hablemos de cosas dolorosas, pero entonces, ¿quién es el experto? El medio de comunicación define al entrevistar a alguien quién es el experto, cómo, y sobre todo lo que nosotros estamos trabajando, la utilidad del experto. Porque la meteorología, en el periodo que nosotros estamos trabajando, no le sirve a los agrónomos. No les sirve, o sea, los meteorólogos lo que hacen es decir cómo fue el tiempo ayer. Yesterday. Ayer. Entonces, los agrónomos quieren saber qué va a pasar mañana, la próxima semana, o en algún momento del futuro. Entonces, son expertos los que trabajan en los departamentos de ciencias en las universidades. Son expertos lo que la prensa determina, digamos, como experto para entender cómo funciona el tiempo. Eso es lo que estamos trabajando. Y estamos, evidentemente, trabajando con conceptos de expertise. ¿Qué es un experto? ¿Cómo funciona la experticia? Y ahí nos hemos perdido durante un año pensando en eso y no hemos llegado absolutamente a ninguna conclusión, debo decir, porque hemos estado mirando este tema. Ahora, los avances, si tengo un tiempo, los avances del trabajo principalmente, ustedes saben lo que son los fondos, ¿no? Entonces el primer año es como archivos, ese tipo de cosas. ¿Sí? Entonces, ¿cuáles son los archivos donde aparece esta información? Primero el Archivo Nacional, el Observatorio Astronómico, para mirar las redes, y después, ¿no es cierto?, hay una particularidad. Una parte, apart this methodology is through German scientists. Entonces, los investigadores alemanes que forman el Instituto de Meteorología dejaron cartas, letras, muchas cartas. Y entonces, con el auspicio del Estado de Chile, ¿no es cierto?, yo viajé a Alemania a buscar esas cartas. Bueno, Están en el Leibniz Institute para geografía, otras en la Biblioteca Estatal de Berlín. Y entonces están las cartas de un personaje en Chile que se llama Walter Knoche. Walter Knoche is very important in this history. Entonces, Walter Knoche tiene relaciones con físicos como Ernst Gerke, Julius Elster y Hans Geitel, que son físicos bien importantes para la construcción de lo que entendemos hoy día también por el estudio de la meteorología y del clima, y también con meteorólogos como Gustav Hellmann y geógrafos como Hans Mortensen. Entonces, primero tenemos las cartas, después tenemos que, fascinantemente, las cartas están escritas a máquinas, entonces no hay problemas con la letra, están en alemán, por supuesto. Y entonces tenemos que descubrir si este personaje, o sea, estamos buscando eso, Walter Knoche, qué relaciones tiene con esta red en Alemania para construir su disciplina. Y podemos encontrar algo bien interesante o divertido, o no sé, que él tiene un gran vínculo con los físicos para entender cómo funciona la meteorología, pero él, como director del Instituto de Meteorología, hace otra cosa completamente diferente. Porque tiene que seguir los cánones, los criterios burocráticos de la Universidad de Chile, que los conocemos, ahí. Me imagino, eso puede ser un problema. Entonces, esa es nuestra situación en este momento del trabajo, y estamos viendo cómo coordinarnos para hacer los papers. Thank you so much.
Gracias, Carlos. Bueno, Carlos, como ustedes saben, es el director de este proyecto Fondesit y es profesor de la Facultad de Filosofía y Humanidades. Entonces ahora vamos a pasar a la charla de hoy de Paul Edwards, que es el director del programa de Ciencia, Tecnología y Sociedad de la Universidad de Stanford. Paul escribe y enseña sobre historia, política, cultura y las infraestructuras de información. Y uno de sus libros que tiene relación con lo que vamos a ver hoy día se llama A Vast Machine, Computer Models, Climate Data and the Politics of Global Warming. Hay mucho más, pero mejor yo creo pasamos a la charla.
Go. Well, so thank you for having me here today. I think you could probably tell me much more than I can tell you, but I will do my best to at least entertain you for half an hour here. Let's see. We're a small group, so I am very happy to be interrupted. And if you want to discuss amongst yourselves, you can do that at any point, and you need not speak English for me. I understand slightly, but I do not speak in a efficient way, so I'm not going to try. And if I tend to talk fast, so if I get too fast, please signal me and ask me to repeat. I'm really happy to do that. So there's so much I could talk about, and the period that you're interested in is not the one I have done the most work on, which is mostly post-1945 computer era climate science. But I do have a lot to say about the history of meteorology, and yeah, here we are. Okay. Yeah, and I'm sorry about the noise too. I'm immunocompromised, so I try to minimize my exposure to COVID, but okay. we need to be able to hear. That's fine. Yeah. Sounds good. Sure. Yeah. Good. Yeah. Yeah, that's probably good. Okay. So, I mean, again, probably telling the people in this research group things they already know, but measuring instruments, especially barometers and thermometers, are kind of the base of meteorology, but also wind is, especially in the Straits of Magellan that you were talking about, the southern Chile, places like that, they're very important. And one of the first big moves in international cooperation around meteorology was in 1853, organized by Matthew Maury, who was a retired Navy sea captain, who wanted to standardize measurement of all kinds of meteorological variables at sea so that he could make better maps of winds and ocean currents. So he held a meeting in Brussels, and many nations agreed to do this, and these ship logs began to come back to him full of measurements of wind, pressure, temperature, sea surface temperature, other important variables. And those were incredibly important and valuable, not just for meteorologists, but especially for sailors, because the maps that Maury created allowed them to cut 30 days off the voyage from England to San Francisco. That is an enormous amount of time before the canal, So this has happened again and again in meteorology, that it's actually it's one of the sciences that creates the most social value. We spend much less on it than it returns to us in things that we can use for farming, for travel, air travel, and so on. So the biggest event in the history of meteorology, really, in a lot of ways, is telegraphy. So starting in the 1820s, but then really picking up steam in the 1850s and 60s, you get telegraph networks that are international and intercolonial, because, of course, it's the colonial era, and a lot of the telegraph lines go to colonies of the Portuguese Empire and the British Empire and others. So weather data are small relative to as pieces of information. And one of the most important things that happened then was that telegraph operators agreed to send weather data for nothing over the telegraph systems. So data exchange was free. And that became a tradition that really lasted until about the year 2000. I'll talk about that more later. But that free sharing of data meant that it was possible to get pictures from the telegraph of weather over very large areas, whole continents, and even more. This is the period when state weather bureaus are formed and exchange happens across borders in Europe. It's a lot like the Postal Service, and everybody benefits if there's a flow of information in both directions across a border. So, even as early as, this is 1872, this is a US War Department weather map. You may not be able to see it really well, but you can see a high pressure zone there kind of in the center of it. And then the little circles that you see in some places are the stations, the weather stations that are reporting these data. And one thing you can see is there are not a lot of them. So they're producing these weather maps, but the accuracy is quite low because they're really only seeing a very abstract view of what they're looking at. There's a meeting of weather service directors of the US and mostly Europeans in 1873, but then they meet again and form the International Meteorological Organization in 1879. And this organization lasts until after World War II. Its main job is for the weather service directors, who are often independent of the government in the sense that they work for the government, but they are not, their weather business is not considered something that the government should be part of. They meet and they try to decide on standards for everything. So temperature, you mentioned different temperature scales, there are different pressure scales. One of the biggest issues is observing hours. And so the idea is you would have regular observing hours, but what should they be? And every country has its own set of standards. And the organization is really very weak because it's really mostly weather service directors sending letters back and forth and sometimes meeting. And they kind of urge each other to adopt standards, but it's very slow and it doesn't work very well. but they do make some progress. So this organization's, the largest budget it ever had was about $20,000. So that's not a lot of money. It was not a, not a strong, powerful thing, but it was at least a movement in the direction of international standards. There we go. So here you can see the evolution of coverage by surface stations. Now, so the rings around a station on this map have a radius of 500 kilometers. So this is, each station is representing quite a large area. And you see that most of them are in Europe. There's some in the eastern United States, and then a few in Australia, Southern America, South America, and southern tip of Africa. But there are large areas of the world, especially Africa and Central South America, that are just not covered at all. And then that changes quite quickly as weather knowledge becomes more important and valuable. And then by 1960, most of the world has coverage by surface stations, at least in some sense. Now, connections to climatology. Climatology is the word that was used really up until about the 1960s to refer to the study of climate. And it was mostly a geographical discipline. So the idea was climatologists described the climates of a particular city or a region or a continent, and there were typologies of climate, desert, Arctic, etc. But they didn't do a lot of measuring. It was mostly descriptive and qualitative. This is an example of an effort to collect records of climate for the world. And the thing that interests me the most about this is that, so here it starts in 1891, we're in East Africa. And you see they're just taking the daily maximum and the daily minimum and dividing by 2 to get and then for an entire month to get an average temperature for a month. It's a perfectly reasonable way to do it at that time. But an interesting thing about this way of handling things is that this is what was reported to the central collectors of the world weather records. And before that, the Réseau Mondial, which means worldwide network, and was the first attempt to get a global climatological system going. So if you think of this just in terms of calculation, this was an effort to push the calculation onto the local observers who had to do this, adding up of all these daily maximums and minimums. This is an era before computers. So they're not reporting every measurement. They're reporting their summary, their statistical summary of measurements. And this is the kind of thing that later created a lot of problems for climate science as it began to look backward and try to reconstruct the climates of, the observations of the past. Because what they would really like to know is exactly what was observed and what time of day and where and with what instrument and all kinds of other things we would now call metadata that were simply not recorded by these observers. Right. So in some cases, that's what they've done, is they've been able to go back and find those original records and recalculate from scratch what they found. So here we are in 1914, and already maps like these are being published on a regular basis. And so we're looking at the world from the North Pole. And some scientists objected to the publication of maps like this because they actually contain very little data. So in a way, there's a kind of a meteorological fantasy here they have a few data points and they've got some knowledge of winds and pressure. And so they are drawing lines that seem to indicate what's going on, but they're really not very well supported by underlying data. But it's interesting that they were able to do this on a hemispheric scale. And by this point, it's well understood that that weather and climate are global systems, and especially around that the polar areas are really important for the climates of the middle latitudes. So they're starting to try to map it out and record it. This is probably my favorite episode in the history of meteorology or climate science, really. So Louis Fry Richardson was a conscientious objector during the First World War. He was assigned to drive ambulances, but his hobby was meteorology. And by then, the equations of motion and state of the atmosphere had been well defined by Bjerknes, Norwegian, earlier. And he decided he would try to create a system for calculating weather, for doing a numerical weather forecast. And this is a beautiful graphic that is done much later in the 1990s by a Belgian artist, but it shows exactly what the idea was, is a huge spherical stadium filled with rows of seats, and each person in a seat has a calculating machine. And their job is to take a calculating form that Richardson designed, and each one is calculating what's happening in a little piece of the atmosphere for the whole world. So you'd have, one person is here is representing Santiago and doing the calculation for this place, and then handing off their calculation to the next person in the line. And in this way, with 64,000 people, he thought he might be able to predict the weather about as fast as it actually happens.
If you read that in the book,
Oh, yeah.
at the end of the book, it's going to be function. And you remind you tell that in the middle there is this pole. In the top there is the red
Yes.
with the line, the lantern.
Yeah.
That is pointing to the area with a red light if they are going too slow.
Right.
Not
Right.
the area.
Yes. Yeah. Sort of the conductor of a meteorological orchestra.
Yeah.
Yeah. And the thing, so, I mean, this is very well known, but so he did this, he developed all these computing forms that would allow this, and took data for a particular day and tried to make an 8-hour forecast, and it was wildly wrong. And it was wrong not because there was anything wrong with his calculation, but because of a computing phenomenon that was not understood until the 1950s of what happens when you do repetitive calculations with large numbers. So one of the things concepts I've used in the book I wrote about climate science is, and this is also about meteorology, is this idea of a frictional force that data exert on our ability to understand, to project weather or climate in advance. And you can kind of see it in this series of images. So up on the right, you have a steamship with its recording by hand of various measurements. And here's a weather telegram with a few numbers in it. That's faster than the manual form and can be moved around more quickly, but still at every station where it stops, it has to be transcribed by a human being and then sent on again or used there. And there's just endless copying, transcription, addition and subtraction that has to be done over and over and over again at every place. Then we get to the punch card era, which people associate those with digital computers, but they actually are much earlier. They go back into the 1890s and were first used in meteorology in the 1920s. And there was even a Czech scientist who volunteered to punch all the data for every country in the world on punch cards. Nobody took him up on it, which was lucky for him, but these were then, the basis for early computer data recording as well. And then finally, so this, I just love this story. So now we're in the 1950s and we're in the US National Weather Records Center, where all the weather data that's ever been collected in the US is recorded on punch cards. And those cabinets you see are filled with punch cards, and they're in the entrance hall because they've run out of room elsewhere. And they're beginning to worry that the building will collapse under the weight of all these cards. So what are we going to do? And fortunately for them, this is just about the time when digital tape became available and is much smaller. And then for many decades, there was this problem of moving tape from one format to a new format as the tape machines changed and the recording formats changed. And it was incredibly expensive and slow. So computerized numerical weather prediction begins in, almost right after World War II. It's closely tied to studies of atomic weapons because both of these problems, the movement of a fluid, the atmosphere, and the movement of a fluid and exploding shock wave, use very similar equations. So the people who did these things some of them were the same people. Some of their students were educated using the same textbooks for atomic weapons and meteorology. And the first computer weather forecast was done in 1950 on the ENIAC, which was a really primitive machine, not even really what we would call a computer today, but they were able to use it. And it was surprisingly successful. And it used a method that was very similar to the one that Richardson used. And Richardson was actually still alive at the time that forecast was made. And when the team finished that work, they called him and said, we did it and it worked, which must have made him very happy. Right. So there's also work on this in Sweden and Norway, especially, and some movement of Norwegian and Swedish scientists back and forth from the US and routine forecasting by 1954 in Sweden and 55 in the US. So, this is just a basic diagram of how a computer model of the atmosphere works. Still the same system Richardson designed in a lot of ways. Divide up the atmosphere into a bunch of grid boxes, calculate the movement of mass and energy and momentum from one box to another. You do it on a time step, typically every 10 minutes. The grids can be very, very large in the case of climate models and very small down to the level of 1 kilometer or so in a weather model today. And over time, this has gone from being 2-dimensional to being 3-dimensional and to covering longer spans of time and many, many more physical processes. So at first, it's really just, temperature, mass, humidity, momentum, but gradually they've added, particles and greenhouse gases and all the other things that matter in climate. So this is, I don't know if this will work when I click it. I'll try to click it and we'll see, but this is the earliest climate model I know of. It was actually written in 1957 by this guy who was a graduate student at the time at the Lawrence Livermore Lab. He wrote the program for it on a computer that the lab did not have yet. So he wrote it using the manual for the programming language without ever testing it on a real machine until the computer arrived. Let's see if it will show. Nope. I would have to click on it with a mouse. But click on the image itself. She may not be able to. Oh, yeah. No, back up. But no, not working. Yeah, there. Ah,
Y le voy a hacer clic en la imagen.
there you go. Beautiful. So what we're seeing is the diurnal tide. So each rotation, it's the Earth rotating and the atmosphere rising when the sun comes up and sinking when it falls as it gets cooler. So he made this with an animation camera, just by printing out, hundreds of copies and then shooting them one frame at a time and turning it into an animation. And this was really impressive to the other climate scientists of the day, because they, for them, output was almost all numbers without any images. And here they were seeing the result of a modeling exercise. So one of the big issues for all kinds of, both weather and climate modeling was that models use regular grids, but weather stations are not located at grid points. So there's an enormous numerical issue with taking observations from the places they actually happen and interpolating to the points in the grid that the model needs. And this continues to be an issue for all kinds of modeling, that there are many schemes for doing that interpolation. But you can see how, there are some places in the world where observations are very sparse. This one in particular is interesting because this map, I believe, is around 1954, maybe 1957. But if you look at China, which is in the top of the map, you see it's largely empty. And that's because after the Chinese Revolution, China withdrew from the world meteorological system for a good 15 years and just didn't report its data. So there, and also in the former Soviet Union, there were these expeditions to go and retrieve the data that they had, but had just never shared later on. So computers, of course, have been the other, after the telegraph, the other revolution in climate science and meteorology. And what you see here along the bottom of this chart, you see new computers coming into the National Weather Service in the US year by year, and the steady improvement in the forecasts, so that in 15 years' time, the 72-hour forecast becomes as good as the 36-hour forecast was 15 years earlier. So over time, they've just gotten better and better, and now it's quite often, in many places, possible to get a 15-minute forecast that is very accurate. Depends a lot on the topography of the area, but it does work for many places. So, just looking at what Carlos outlined earlier about your project, I mean, a lot of this is happening in periods that are later than the one you're concerned with, but it starts already with the international meetings of the 1850s and beyond. Meteorologists, it may be the first science that really understands itself as global, because you at least need hemispheric information to make a good weather forecast. Weather moves fast. You can make a forecast for 48 hours with a barometer and it will be pretty good for where you are. But if you want to look out 5, 6, 8, 10 days, the weather is going to move all the way around the hemisphere in that amount of time, and you need to know what's going to happen. So after World War II, we see a whole long series of new motion in the direction of global infrastructure for meteorology. So WMO, begins really around 1947, but officially founded in 1951 as part of the United Nations. Then you have the IGY, the International Geophysical Year, kind of that was in a way the third polar year. It was supposed to be a polar year, but turned into this whole global study. Fascinating thing. So from a meteorological point of view, what they did was they had chains of observing stations that went from pole to pole on 3 longitude lines. So, and they were doing vertical observing too, with balloons and airplanes. So they're trying to get a kind of cross section of the globe at 3, sort of 120-degree intervals around the planet. And those data were studied for decades after the IGY as a way of getting that kind of vertical image. And then we have many other things too. The World Weather Watch is a system, up in the top left, a system the WMO started to develop in the 50s and really is still there as the global observing system that takes in data, sends it to central calculating centers, which make forecasts for the whole planet, and then redistributes those to national weather services everywhere, which do their own calculating with those. Right, I talked about this a minute ago. And so this is also when we get the first continuous measurements of carbon dioxide, starting in Antarctica and then at Mauna Loa in Hawaii. See, I'm talking much longer than I intended to, and I really mean it if you want to interrupt and jump in, but I think I only have a couple more slides here. So this is just a fascinating little piece of political history that one of the least known elements of the atmosphere in the 40s and 50s, they're developing these global models which have a vertical dimension, but they really don't know very much about the atmosphere high above the ground. They just don't have much data. So this nuclear weapons tests gave them a tracer material. So the radioactive dust from these things would go high into the stratosphere, and they were able then to measure it at, in Marshall Islands, which are close to the equator. And then one of the big questions was, is the northern hemisphere connected to the southern hemisphere, meteorologically speaking? Because there is this kind of pattern where the air rises and falls to the north and the south and doesn't do much at the equator. So if there were a nuclear war, would people in the southern hemisphere be affected? So they did these tests, and then they sent balloons and airplanes up to measure, and the answer was, yes, it does cross the equator. Yes, you too will be in trouble if we have a nuclear war. So let's see, I think I will skip over this. Just say one word about this. Really amazing thing. So, you collect a lot of data and you map it, and we've seen weather maps with isobars and iso lines of other kinds. But this use of computer models to bring data into forecasts as they are reported, instead of once every 6 hours or 12 hours, which was the pattern before, was really a huge revolution. And it's still the way things are done today. Right. So today we live with this system that was begun in the 50s. It's very elaborate. Part of its fascinating history is what they did in the 60s and 70s before the internet to exchange data around the entire world. And it is really a complicated kludgy system with microwave relays and telegrams and mail and store and forward. So data being reported to one place and then redistributed everywhere else over and over and over again, faxes and on and on. But today it's just completely routine, and this is where our weather forecasts come from now. Let's see. So I'll say a little bit about reconstructing data from the past. And this slide is a little hard for you to see from here, at least, but what you're looking at are precipitation gauges in different countries where the Weather Service in a particular moment changes to a new gauge, a new design. So made by a different manufacturer, maybe a different design. And in each case, you can see there's a stepwise change where the new instrument measures a little more or a little less than the previous instrument. So the climate hasn't changed. The amount of precipitation hasn't changed. The instrument has changed. And if you know that, and you know what the difference is between the old instrument and the new instrument, you can calculate the difference because you could just add a factor to take account of it. But if you don't know all these things, the data you're looking at are less accurate. So a lot of the work of climate science has been to go back and look at older data, try. Yeah, so here's another example of data friction. So this was a study where they're taking data like that Zanzibar data I showed you earlier, and they're looking at different countries and seeing at different places, they're using different systems to calculate the daily mean, often in the same country, sometimes over time, but sometimes even at the same moment, they'll be using all these different systems. So then they have to go back and try to recover the original data and recalculate. Okay, so let me wind up here. This is from the 2007 IPCC report, and you're seeing a series of different calculations of global temperature starting in 1881. And of course, they cover different time periods. These are made, and one of the remarkable things is they actually match pretty closely, especially after 1900. But how are they making these data sets? And we see that, in 1881, it's about 100 stations, and then really up into 1960s, we're still in the low hundreds of stations being used. And then we get computer ingestion of data and computer calculation for the first time. And so then we start to see many more stations being able to be used. And today, I mean, the last one on the list there now covers something like 45,000 stations. And it's done all this recovery of historical records from stations that were never included in the past because they had gaps. Okay, I've said way too much. I'm really sorry I went on so long, but I hope that had some interest for you and maybe some interest for your project, and let's talk.
I think since we are not that a large group, we can open the discussion. I don't know if some people from the project would like to say something, like Nelson or Jose or Carlos. If not, we can just open the conversation better. I think we'll, yeah. So the thing is, tenemos que usar el micrófono por el Zoom. ¿Sí?
Thank you so much for the talk. Yeah, for us, it's very important. I think the relationship between the different centers or observatories, centers. Not only the relationship, but how the data circulate.
Right. Yeah.
And we have in Chile many institutions, university, but it's very important the se me olvidó cómo se dice la palabra, ferrocarril, train stations, because the train station was with telegraph.
Yes.
Only.
Right.
Yeah. The best meteorological or the best the data was in this place. Hmm? And my question is how study we can study this relationship. There was center of calculation, maybe like Bruno Latour, say. That's it, my first question. How we can study this circulation? Another question is about the maps. Meteorological maps. Because in this circulation is very important. Not only this is center of calculations, for example here Universidad de Chile, but another places like Punta Arenas, for example.
Right.
So also.
Vamos a recolectar algunas intervenciones.
Okay.
Sure.
Yeah, thank you for the talk. I just wanted to make a few questions or points. First, I disagree that meteorology is like the first science to consider itself global. I mean, I think there are many sciences because human nature and rankings, they all want to be the first one, right? For some odd reason that I cannot understand. So, and astronomy was also, I've seen that in many places, like this is the first science to be really global, and the International Astronomical Union has existed for many, many centuries and whatever. I don't know who is right, and honestly, I don't care, but it is like.
I've had seismology suggested as another candidate.
Also seismology, it's you're right, so I don't know about that. Huh? Could be. The other thing I wanted to say is that I thought it was interesting, the map you showed about the stations of meteorological stations. There was like this curly circles in the map, and in the 60s the map was practically covered, and it was very interesting because it's actually like the same path that goes with the telegraph lines.
Yes.
The shape is different. It's not like these circles, like this curly hair on the map. It's like a different shape, but it's basically the same. So it was very interesting. And what I wanted to ask is, I mean, you know a lot about the history of this science, and you also run a program on STS.
Yes.
So how do you think the both like history of meteorology and STS could contribute to understanding this subject?
We stop there. So
Sure. Let's see. Let's see. So trains and telegraphs and maps. Well, your colleague is absolutely right. You know, telegraph lines typically followed train lines because that was where they could get an easy right of way, and also because the trains needed them for scheduling, for signaling, so they wouldn't run into each other. You know, imagine this is true in most places, but early trains, there was only one track. So when you were moving, if another train is coming the other way, you had to pull out onto a siding and wait for the oncoming train to pass. And you could only do that if you knew the train was coming. So there were terrible accidents because of signaling failures. So telegraph was a huge importance to them. Let's see. What is the question about maps in particular for you?
The information.
Right.
Without information.
Right. Well, badly is the answer. But you know, my sense is that there's a long period when a lot of what's going on in weather prediction is that they are using previous maps that were confirmed by events as a way of as analogs for a situation they now see. So if they get similar data for a particular day, they're going to predict that it will evolve in the same way as another system that they've already seen. So some weather services relied heavily on files full of old weather maps, and people would develop these incredible pattern recognition skills and sort of say, oh, this reminds me of May 4th, 1895. And so they pull out that map and compare it to the map they had today and use that as a base for a weather forecast for the coming days. I don't think that answers your question very well, but forgive me, I need to get yours back, recover your question as well.
Yeah, the first two were just comments.
Yeah, right. Yeah.
I was curious about how you think you could bring together, or how you actually.
STS and history.
Yeah, we're working on this already.
Right. Right. Yeah. Well, I mean, part of my observation about the STS literature, such as it is about climate change, is that way too many STS researchers are afraid of science. And, meteorology is a very complex mathematical science. And I don't understand all the math myself, so I'm not going to pretend that I do, but you got to be willing to get over that hump and talk to the meteorologists and the climate scientists about what they're doing and how they understand it. So, I mean, STS, the big strength of STS has always been case studies that have a kind of ethnographic side, even if they're not really ethnographies. And I think those are, very, very valuable. The history side, of course, is harder because we can't talk to those people, they're dead. Well, yeah, maybe you can succeed at that. Maybe you have a new method that we should know about. Right. And there, it's just the meticulous work that you're doing with letters. And I mean, so much of the climatology of the turn of the 20th century was done by mail. I mean, and I spent some time reading the Réseau Mondial background. So this was the British effort to collect. They were just trying to get climate records from one station in every 10-degree latitude longitude square. Just that. And the typical delay from request to publication was 7 or 8 years, and sometimes as many as 15 years. And often it would be because they had sent a letter asking for these records and they came back, but not in the form that they needed them. So then they had to write back, and it took months for the mail to travel to remote places, and then the return trip, and on and on and on. So, some of those records still exist. A lot of them we only have the accounts of them and not the actual records. So I love what you're doing, and there are, British projects on similar kinds of things. And Austria, Deborah Cohen has done some amazing work on Austria, which was, one of the great climatologists of the end of the 19th century, early 20th, was Julius von Hahn, who wrote the textbook on climatology that was used for like 30 or 40 years around that period. And she's written some great stuff about how he thought about climatology then. But, I think STS is going to be dominated by the urgency of the climate crisis that we're in now. And so it's not going to end up thinking as much about the history of climate science as I think it should. Yeah. Mm-hmm.
Thank you very much. Dear Paul, I am happy to stay here after several emails. Thank you very much to Cecilia for organizing this meeting. I am a part of this project, and I am in charge in the topic of the solar energy. And in this sense, I have a question for you about the 20th century, thinking that for the 19th century, the solar information, the solar radiation was very important for 3 people in Europe. Now, at the beginning of the 20th century, was matter for the Smithsonian Institute. No, but in the 20th century was confirmed most strong organization for the measures of the solar radiation in surface of the Earth, and there were organizations that maybe you knew something about this. Now the solar radiation balance data was placed in Leningrad, now in Soviet Union, in the Cold War. No, that means many things. No, have a meaning, but as far as I know, this organization simply it was banished. And I didn't have any information about the finish of this solar radiation database or something like this. And in this sense, your presentation allow us some kind of continuity in the time, but for solar measures, the matter is it was an intermittent duration of the organization, societies, the collection of data, etc. Then I would like to know something about your perspective about this, in the sense that the science is not only increasingly many times the people forget or the history before. Thanks.
Yeah. Oh boy. Well, unfortunately, I know absolutely nothing. Well, not absolutely nothing, but almost nothing about the history of solar radiation measurement. It's a topic that comes up a lot in the IPCC because there are these, kind of periods when you get, solar minima that seem to influence the climate in a pretty big way around the Little Ice Age and things like that. But I really don't know much about the history of measurement. I wish I did. You'll have to tell me. Yeah.
Paul, in a minute, I would like to ask you a question going again to this relationship with STS, since this is a school of government.
Yeah.
You said, well, STS people, researchers should really get into that science and that the technologies associated, and here we have several of those scientists. So when you do that, which you have done with the limitations you said you have, what do you learn? Because your book says politics, power,
Right.
which is very it calls the attention to a school like here. So what do you learn when you go into that science?
Well, for one thing, I got to say that, I haven't tried every science in the world, but meteorologists and climate scientists are some of the nicest people I've ever met. And, oh yeah, almost all the time. And they love to talk about their science, and they're actually quite good at it. Most of them, not everybody, but if you need some basic knowledge about things like how computers work and what they can do, and the nature of numbers and sort of basic units of measure and things like that. But if you haven't, even that kind of basic background, and you just start to talk to them, they will tell you what their problems are. And from a political point of view, the most interesting thing to me was that as soon as I started interviewing people, and I interviewed 80 plus climate scientists for my climate book, nearly everybody led with this. Well, we're very uncertain about this aspect of climate science, but here's what we know. And as a political move, that is a disastrous way to start your conversation. You basically say, we're not that sure, but, So I've actually spent a lot of time, as I've gained more knowledge and ability in this area, talking to them about that and saying, no, lead with what you know, and then put the error bars around it. Don't lead with the error and, and expect that to be convincing.
Sorry.
Yeah, please.
Know how science works.
Right,
And science,
right,
always, I mean, launching concept forever.
right,
And it doesn't work like that.
right,
And they assume we know that's not science.
right.
I think there's a problem with the science.
Yeah. Well, yeah, go ahead.
So yeah, I was wondering whether you could tell us a little bit more about the relationship between the development of math as a discipline
Yeah.
and mathematicians
Yeah,
and meteorology, because it seemed
Oh,
like,
yeah.
I don't know anything about meteorology or climate
Right.
science, but it seems like at the beginning, you have the problem of not enough data, but I'm assuming that with time, as happens in many other areas of science, the problem is you have a lot of data and you're not able to actually process it in a meaningful way. So how did that change? And what was the relationship in the development, first of all?
yeah.
How has that changed
right.
in meteorology?
Well, I mean, so John von Neumann, who was one of the great mathematicians of the 20th century, was also worked for the Los Alamos project and helped design the atomic bomb, and also worked on the computers at Princeton University, designed one of them. The architecture of modern computers is mostly von Neumann architecture. So, sort of colossal genius. But the biggest contribution he made to mathematics was development of methods of solving nonlinear equations using discrete math. So instead of, it had always been trying to find a direct solution to a nonlinear equation. And with all the ones that are going on in meteorology, you can't do that. So that's why you have to model, because you can only do it on very short, by making lots of little calculations of, the area under a curve, that kind of thing. So this was unknown math before von Neumann and his period. And it contributed to many, many things. So your other question is about when you get large amounts of data. Really, in a lot of ways, the biggest issue is what I mentioned during the talk, which is interpolating between data points and how you weight them relative to each other, because not all data are of equal quality. And a fascinating thing about the way weather forecast systems work now is that they sometimes will discover a problem with an instrument in a remote place based on the fact that it doesn't, the measurements it produces don't correspond to what the model is predicting. So the model is actually better at making data than the instruments are. And there's a lot to say about this, because this really blew my mind when I started to understand it. What happens today is that in a weather forecast, the initial data are taken from the previous forecast. So whatever the previous forecast says is supposed to be happening 6 hours from now, you start with the forecast, not with the data from instruments. And then you use the instruments to correct the forecast. So the instruments are really playing a secondary role. The data is in the model, not in the instruments. And, again, this just boggles my mind, but it's because there's so much of it. And some of it, a lot of it today comes from satellites. And satellites are, as a mathematical issue, are really kind of a stunning thing, because, if you think about it, we have like a station on the surface and it's reading at a point. And then we have weather balloons or airplanes, and they're measuring on a line as they move. But satellites are measuring from space, and all they're seeing is radiation at the top of the atmosphere. So they're also looking at a huge volume underneath them. And typically you could imagine like an 80-kilometer circle as a column going down through the atmosphere. And they're trying to read what's happening in that whole column So they take the radiation measurement at the top and then they model what's happening underneath it. Because in every layer of the atmosphere, there's a different composition of gases, there's a different density. So all the way down to the surface, what's really being produced is modeled data that then go into the weather models, and yet they're extremely good. On the climate side and the politics side, this is a fascinating thing because originally there was only one group that studied this instrument, the microwave sounding unit that brings back this column radiation data. It's at the University of Alabama at Huntsville. So this group collected that data, produced these data models, and put out the data for the rest of the world to use. But over time, they've discovered all kinds of problems in the way that they model it. So for example, satellites, the orbits decay over time. So the angle of observation starts to change as the satellite gets lower, and you've got to account for that. One satellite is replaced with another. It's a slightly different instrument, so you've got to account for that, and on and on and on. And there are a million things like that that had to be accounted for. So eventually another group began to take the same data and analyze them. And this is all relevant to climate change because these Huntsville guys, one of them is a creationist, which just blows my mind. It doesn't believe in evolution. And he also really, really, really wants there not to be climate change. So he keeps saying, our instruments show that actually the atmosphere is not warming. But then this other group comes along and they start to find all kinds of issues with the way the first group is doing the analysis. So now we have a kind of data competition. And the first group gets closer to what's measured at the surface and in the very lower part of the atmosphere. And, this continues to this day. There's now even a third group doing the same kind of analysis. And this is great. But, part of what it shows is the importance of having lots of different groups treating the same data because, nobody's ever completely right about anything. Sure.
No. It's really very interesting, this talk, because it makes me think about the development of meteorology throughout the years, and to realize how important it was for the progress of meteorology, the development of other areas in technology and science.
Mm-hmm.
Communication in the 19th century with telegraph, but mainly in the middle of the 20th century, the satellite technology that evolved very quickly, and computer science.
Yeah.
Without the development of computer science, meteorology wouldn't be like it is today.
Yeah.
But the other idea that make me hearing your talk is the very quick, I will use this word, deshumanization of meteorology.
Yeah.
Deshumanization.
Yeah.
And I can imagine, maybe I will not see it, but maybe the young generation will see it. In 50 years more, meteorology will be run by artificial intelligence.
Oh.
With no presence of human being. I started working in meteorology in the 70s, and I had the opportunity to tour the country, visiting stations. In each of them, there was an observer. That was the main person that keep meteorology going. More and more, you will not see anymore these observers.
Yeah.
The typical observer has been replaced by an automatic station.
Yes. Yeah.
There's no more people, and then people is disappearing. People now is watching the output of models.
Yeah.
And the truth is there. And now, for example, here there is a specialist in modeling. And at this time, the truth in meteorology is not one observation, it's the reanalysis.
Yeah.
Reanalysis is the truth. We have to everything is based on reanalysis.
Right.
And reanalysis is a combination of many things: observation, computer science, computer output of models.
Yeah.
And then do you have this perception that
Oh,
meteorology
totally.
is very quickly going to one of the first science that is absolutely dehumanized?
That's fascinating.
Astronomy too.
Right. No, I think that might be absolutely right. I think it might even happen faster than that in 10 or 20 years. Phaedra Daifa wrote a really great ethnography of a weather center. And this came out 7 or 8 years ago. And, at that time, in her ethnography, there's still an important role for human weather scientists in weather stations, not in stations, but in projections, because 90 or 95% of the computerized forecasts are dead on right. But it's the moments where there's an extreme event, a really unusual situation where the human forecaster would come in and say, no, the computer's screwed it up. We're going to issue a different forecast and be right more often than not. But that percentage has been shrinking, and it would be totally unsurprising to me if you were right in 10 years or 20 years. Just no more humans in the whole system.
Thanks, Paul, for your presentation. I have 2 questions. I know nothing about meteorology in the 20th century. I have been studying in the 19th century,
Okay.
which is very different from what you present here. So my question is about the meteorologist itself as a subject. I'm particularly interested in the expert knowledge, lay knowledge, and amateurs in meteorology. So my first question is, what defines the expertise of a meteorologist and a climatologist in the computer era? And my second is, what do you think is the main difference in the expertise of meteorologists and climatologists in the 19th century?
Well, let's see. So let me take the last question first. I think that toward the end of the 19th century, with Hahn and a few others, you begin to see real theoretical climatology that's based on, the sun and orbital patterns and things like that. But really, before that, I don't think there is a lot of climatological expertise. I mean, there's geographical expertise in the sense of knowing about a region and its climate, but it's not measurement-based science. That comes really in the 1880s, 90s with Hahn and a handful of others, and then yeah.
A model, a mathematical model, can be considering a point of expertise of climatologists?
Yeah. I mean, well, not just mathematical, but astronomical, really. I mean, it's sort of understanding what the relationship is between the sun and the atmosphere and the ocean. And I mean, a lot of the problem for climatology, I didn't talk about this much, is that the biggest influence on global climate is the ocean, and it's just much less well known even today than the atmosphere is. It's harder to study, and it's gigantic and it's deep and all that. So there were, Heinrich Dove back in 1853 used ship's records to draw kind of isotherms for the whole planet, and then the the research ship Challenger is an amazing story about a 3-year scientific voyage all over the world, and depth sounding and measuring everything wherever they went, and really still the foundation of a lot of climate knowledge about the ocean. Let's see, but so what defines an expert in the computer era? Well, so for meteorologists, it takes a long time for the kind of human aspect of weather forecasting to disappear. I mean, the people are still playing a very large role in defining weather forecasts well into the 70s. A lot of them are doing it on television, and there's kind of a premium on images. And then we start to get these commercial weather services, and their main value is adding imagery, reporters outside looking at hurricanes and taking, watching their clothes blow around and things like that. And they really add a lot of value because they know the local conditions better than any computer knows them then. But starting in the late 80s, we really began to see computers start to eclipse human forecasters for routine forecasting, and the forecasters begin to rely on those. And then, then they have to learn a whole lot of things about computer plots and how to read them, and, how much to trust them, and how much of their own kind of looking out the window knowledge that they can still use in making a forecast. And they do, even in Pedro Daifa's book, there's still people kind of saying, well, go up on the roof and see what's happening, because that's important for our forecast today. So there's there are dramatic changes in the whole field over that time.
Thank you.
Sure.
We will take some of the questions from the chat. Christian Munoz asks, thanks for the talk. And he says, his question is, could you make a comment on how meteorology was fostered by the Second World War?
Oh, how it was changed by the Second World War? Oh, gosh.
Foster,
Was what?
impulse and emotive.
Right.
Yeah.
Yeah. So there have been very few episodes when data sharing in meteorology actually stopped. And one was the First World War, and the other was the Second World War. But even during the Korean War and the Cuban Missile Crisis, data sharing just kept right on happening. It's really kind of amazing. But, in the Second World War in particular, it had enormous value because of airplanes. That was true in the First World War too, but they weren't nearly as important then. And there's the story of the weather forecast for the D-Day invasion of Normandy is one of the most dramatic stories in the history of meteorology, because, the Germans, of course, were making their own forecasts. And the question was, the English Channel is always foggy at that time of year. Is there going to be a moment when the fog lifts and we can invade? And there was a team of meteorologists for the Allies working on this, and they had deep disagreements, but the lead forecaster was a Norwegian, I think, decided that there would be this 12-hour window in the fog, and they decided to launch, and the Germans got their forecast wrong, and that's how World War II was won.
Complementing on that question, I don't know if you have read Alan, there is a paper by Alan and also a book on the history of atmospheric sciences, telling how because of during the Cold War, the arguments that meteorologists and then atmospheric scientists made for getting a lot of funding for the work, to give satellites and all that, give a big impulse to atmospheric science. And that's why those authors think that's why atmospheric science is the leading science in climate change, and it's not biodiversity or other science. Maybe that, I don't know if you have an opinion on that to complement for the question of this, Christian Munoz.
Try the question one more time. So
Yeah, no, I'm just trying to
add on. To
yeah,
this,
if you think the funding that atmospheric sciences
Yeah.
got during the Cold War
Right.
explains in part their development and their leadership in climate sciences now.
That's a long story with a complicated answer. So, first of all, tens of thousands of meteorologists were trained during the war on both sides because it was so important. So that there was soldiers coming out of the war with this training. And then there was an easy appeal to, for more funding for military purposes. But it also coincided with the rise of commercial air travel. So air travel is a whole other story of meteorology. And for a long time, there was kind of a separate forecasting system for commercial air travel between the wars. So it had this kind of huge importance, economically and for travel and for the military. And so a lot of investment was made in training new meteorologists during that period, and then investing in computers and all the scientific work. But another aspect of it was that lost my train of thought there for a minute. Oh, well, so there was also a fascination with the idea of weather control. Mm-hmm. And one of John von Neumann's great articles is something like "Can We Survive Technology?" written about not long before he died. And it talks about the prospect of geoengineering, spreading black carbon on snow to melt the ice and create warmer climates in the north and things like that. Then there was cloud seeding, developed in the 50s. It works, but it doesn't really work. It's an amazing story. And Jim Fleming has an incredible book called, what is it called? It'll come to me in a minute, but it's about the history of weather control ideas, which consist mostly of people shooting at the sky to try to make rain, first with bows and arrows, and then with spears, and then with cannons, and then with guns, and finally they develop cloud seeding, and they think they've found God, but it's really more like it works if the conditions are right, and you don't really know if the conditions are right until you try it.
There is, sorry, Raul, I think it's Raul Valenzuela, I don't know, Raul B, who wanted to do a question on the microphone. But Raul B says yeah. So do we have any question from the chat or no? Well, Raul B. No. Well, if he wants to do it, he can do it, please. No. Okay. Any other question, intervention? Esa. Esa se puede dar, si se puede dar a Alexis, por favor. No. Maybe he can write it if we cannot get the sound.
Microphone is muted.
Yeah. Your microphone is muted, Cristian Simonetti.
Says perhaps too long for another time. Okay.
Yeah. Okay.
Thank you.
Okay. Any other intervention? No. Okay. Acá hay una.
My question it's about the public of meteorology. I don't know, when you showed the 1914 map, the Arctic map, you talk about that the scientists behind it weren't not all were sure to publish it because the data was
Right.
dubious. But my question is that map, for example, that map was about was going to be published to the mass media, to public, or was more circulation in the scientific community itself. And the other part of it, of this, goes about the citizen science and its relationship with meteorology and the development of climate. If you can talk about that.
Yeah, sure. Yeah, both of those are good questions. So the first question is about the synoptic map I showed from 1914. That was a scientific publication, but a fascinating thing is that back in, even in the 1880s, there were maps like that War Department weather map I showed were being published in newspapers, and they were being distributed by fax. So people today think of fax as a digital technology, but it's actually much older and was, developed in the early 19th century and used by newspapers. But the strange thing about it is that the maps didn't last very long. They apparently didn't earn much money for newspapers, so they stopped after 10 or 15 years, at least in the States. I don't know if that happened here, but and then, so your other question about citizen science and meteorology, there's a fascinating story because, of course, there have always been amateur meteorologists who have their barometers and, they write a lot. But the story I like that interests me is Weather Underground. Do you know that system? Yeah. So Weather Underground, it's kind of named after a radical group that bombed some buildings at the University of Michigan in the 1960s during the Vietnam War protests, but it came much later, and it was started by a meteorologist at the University of Michigan in the 90s, when it became possible to hook up your own home weather station to the internet. So it collects weather data from anyone who wants to hook up, and has they have like a long list of kind of inexpensive home weather stations that you can buy, and it knows what their characteristics are, and you report things about its site. And I use it all the time in San Francisco. I can find a station that's 3 blocks from my house and look at what it's reading right now. And I don't trust it like the weather service, but I do trust it enough to decide whether to go for a bike ride. And that system developed into a really strong thing by around 2010, and then it was bought by the Weather Channel. So it still exists as Weather Underground, and it's not just US, it's all over the world. So it's a citizen science project in a way, but now it's also kind of been taken advantage of by a big company to earn money. Anyway, so it's definitely out there.
Bueno, muchas gracias a todos por haber venido, especialmente a nuestro invitado Paul Edwards, a Carlos, a todos los que con hoy día inauguramos el laboratorio en el año, la presencia de la escuela de gobierno y también el proyecto. Así que muchas gracias y espero que nos volvamos a encontrar pronto. Gracias, Paul.
But thanks very much to all of you for suffering through my English, and I wish I could have talked to you in Spanish. And not many people are that interested in this kind of thing, so it's always great to have an audience. So. That's right.